Hi students, welcome to today's class. Today's topic is codes for error detection and correction. Okay, now from this section onwards, we are going to study different types of codes. Okay, so we are decoding some codes or forming some codes which is used for error detection and also for error correction. Okay, so there are different types of code, that is linear block code, cyclic code, convolutional code, compound codes such as turbo codes and parity check codes. So parity check code is also an example for linear block code. So in this session, that is, we are studying about linear block code. Also in module 4, it is dealing with cyclic code, and module 5, it is dealing with convolutional code. Okay, so in this session or in this class, we are learning about what is linear block code. Okay, and what are error detection and correction methods of linear block code. Okay, each error control coding technique involves the use of a channel encoder in the transmitter and a decoding algorithm in the receiver. Okay, so there's a source we have already studied in a communication system. There's a source which produces the symbols SK having a bits of K bits, and this SK bits is given to a channel encoder. So there, for any coding technique, there should be a channel encoder, and at the receiver we have a channel decoder. So here we are discussing about what is encoder and decoder, etc. Okay, so for any coding techniques, we should have a channel encoder at the transmitter and a decoder at the receiver. Okay, so to generate a n, k block code, the channel encoder accepts the information in successive k bit blocks. For each block, it adds n-k redundant bits that are algebraically related to the k message bits, thereby producing an overall encoded block of n bits or n greater than k. Okay, now we are learning about linear block code. Okay, so for a linear block code is generally called n comma k block code. Okay, linear block code is generally called n comma k block code, where n is the size of code word after encoding and k is the size of message bits. Okay, so we are how we are produced. So our the encoding part we are doing to produce n code. Okay, n, a size of n with the code. So here the channel encoder is used for encoding. So channel encoder will accept some information, that is k bits from the source. Okay, that is the k bits from the source. There's a lot of bits, that is called a number of bits are there from source. So these bits are divided into some block. Okay, so this stream of bits can be divided into some block. Each block has a size of k bits. So we are considering a block at a time. So k bit block, we are considering a message have k bit block. So each block is given to the channel encoder. Then at the channel encoder, it will add n minus k bits, that is redundant bits, and this n minus k bits is related to message bit. Okay, so when a block of k bits is given to a channel encoder, the channel encoder will add n minus k bits. It's also called redundant bits or parity bits. This n minus k bits is related to the input bits, that is message bits. Then we produces a n bits. This n bits is called a code word. So the output of encoder is n code word, n bit code word, and the input of encoder is k bit block code, and the encoder will add n minus k bits. Okay, this is very important. So the output n, of course, is greater than k, because k together with n minus k bits gives the n code word. Okay, the n bit block is called code word and n is called the length of code word. Okay, Then the channel encoder produces at a rate. Then channel rate R0 is equal to N by K into Rs, where Rs is the bit rate of the information source. Then the dimensionless term ratio R is equal to K by N is called chord rate, where chord rate R is 0 less than R less than 1, is in between 0 and 1. So for an N comma K linear block code, we have a rate R equal to K by N. If we given K by N, we have N comma K value. Then the bitrate R0 is called a channel data rate. Okay, so that's all about the basics or the parameters of linear block code. So we have linear block code parameters, 3 parameter, that is K block code. So the message information bit is divided to different blocks. Each block has size of K. This block is given to channel encoder. Then the channel encoder adds some block of data, that is N minus K data. Okay, that is called parity bits or redundant bits. Then the output of the encoder is N, that is code word. So these are the parameters of linear block code. Then we can study what is linear block code. So this is channel encoder. We are giving message. So the whole message is divided into equal block having size K bits. Then this block is given to channel encoder. Okay. Okay, the block is given to channel encoder and we get an output that is with having n bit length. And the message block has K bit, and here the channel encoder will add n minus K bit, then we get n bit as code word. In each block of K bits is encoded into a block of n bits, that is n greater than K, by adding n minus K check bits, which is derived from K bits. So we are adding n minus K bits in channel encoder. This is derived from K bits. Okay, message bit. A code is said to be linear. So the output is block code. Now, how it become linear block code? So a code is said to be linear if two code word in the code can be added in modulo to arithmetic to produce a third code word is also in the code. Okay, so it is called linear block code. So if we add two code word, okay, two block of code by modulo to addition, we get third code word. If we add two code word, the code word is the output of channel encoder. If we add two code word, we get a third code word. Then the third code word also inside this code. Then it is called linear code word. So linear block is denoted by n comma k. So n is the code word and k is the message bits. Okay. So consider an n comma k linear block code in which k bits and n code bits are always identical to the message sequence to be transmitted. So the output of n is a part of n is nothing but the input k, and another part is n minus k bits which is added by the channel encoder. The n minus k bit is remaining portion are computed from the message bits itself in accordance with the prescribed encoding rule that determines the mathematical structure of the code. Thus n minus k called parity check bits or parity bits. So we get n minus k from message bit k, and the code word n is the combination of this message bits and n minus k bits, and this n minus k bit is called parity check bits or parity bits. Now what is systematic code word? So the code word have systematic and non-systematic. Non-systematic means it is not in a proper way. So it is an unaltered way. Systematic means it has some proper way of creating a code word. So systematic code word, block code in which the message bits are transmitted in unaltered form is called systematic code. It is not altered form, it is unaltered form. So that is in a systematic form. Okay, so here in this whole section in linear block code, we are representing the message. The message has size k bits as m0, m1, etc., mk minus 1 constitute block k message bits. Okay, and thus we have 2 raised to k distinct message block. Let the sequence message bits be applied to a linear block encoder and producing an n bit code word. The code word is represented as code word size is n. So C0, C1, etc. Cn minus 1. So we have message size k. So message is M0, M1, etc. Mk minus 1. And code word C has size n. Then C has C0, C1, etc. Cn minus 1. Then we have, of course, parity bits, that is B0, etc. The size of parity bit is n minus k. So the parity bit is represented by B0, B1, etc. Bn minus 1. Sorry, n minus k minus 1. Okay, since it is started from B0 and n minus k parity bits. The code to process a systematic structure, a code word is divided into two parts of which occupied by its message bits and other part is parity bits. So in a systematic structure, here this is the systematic structure, a portion is its parity bits and the another portion is of message bits. That is, this is systematic structure. First portion is of parity bits, the other portion is message bits. So the parity bits can be represented as B0 to Bn minus k minus 1 and message bit can be represented as M0 to Mk minus 1. Okay. So the n minus k leftmost bit are parity bits and k rightmost bits are message bits. Okay. Then the code word from this both constitute a code word. Okay. So the size of this is n, this is code word. Okay. So this code word Ci is equal to, first portion is Bi, the next portion is Mi minus n plus k. So Bi is I have 0 to n minus k minus 1. Then the next term is, okay, this is n minus k minus 1. The next term is Bn minus k. Next term is Bn minus k plus 1. So that is the message portion. That is Mi minus n plus k, where I is n plus k, that is n minus k. The next term is n minus k plus 1, etc. We'll have last term is n minus 1. So this is how a code word will look like. Okay. The n minus k parity bits are linear sum of k bits. So we have already said the n minus k parity bits are get from, or we are get it from message bits. So it is parity bits Bi is the linear combination of message bits. So Bi is equal to P0 IM0 plus P0, that is Ij, Pij M0 plus Pi1 M1 plus etc. plus Pk minus 1 I Mk minus 1. So the parity bits are the linear combination of message bits. Okay. So Pij is equal to 1 if Bi depends of Mi, 0 if it is not depend on Mj. So if the parity bits depends on Mj, then it is become 1. If it's not depends, it will become 0. The coefficient Pij are chosen in such a way that the rows or the generator matrix are linearly independent and parity equations are unique. Okay, this is equation 1, this is equation 2. Then from equation 1 and 2 defines the mathematical structure of linear block code. Okay, it is written as, this is M. We have M. These all are a row matrix. We have M is a matrix, row matrix M0 to Mk minus 1. B has a row matrix B0 to Bn minus k minus 1. C has a row matrix C0 to Cn minus 1. Okay, so this is very important. These are the parameters of linear block code. Okay, so where M is 1 by k message vector or information vector, where B is 1 by n minus k parity vector and C is 1 by n code vector. So all these three are row vectors. So we can write B as B is equal to, it is linear combination. So parity bits are linear combination of message bits. So parity bits B can be given from, or can be get from B equal to MP. This is also an important equation. B is equal to M into P. So parity bits B is the linear combination of message, that is M. M is message and P is parity matrix and B is parity bits. So P is K by N minus K. Also the size of P also important. So size of P is K by N minus K. K message by N minus K. And B is equal to MP. So the coefficient matrix is given by P is equal to, we have first I is row and j is column. So first row, so it is always P0, P00, then first row, second column, P01, etc. P0 n minus k minus 1. Okay, so the size of row is k and size of column is n minus k. So here the size is k by n minus k. Okay. So the next row is P10, P11, etc. P1 n minus k minus 1, etc. The last row is Pk minus 1, 0, Pk minus 1, 1, etc. Pk minus 1, n minus k minus 1. So Pij equal to 0 or 1. So if it is dependent with the message, it will become 1. If it is independent with the message, this becomes 0. So B is equal to MP is an important equation, and we have a coefficient matrix P. Okay, and then we are this is the equation for parity matrix, parity check matrix B. Then we want to create the equation for equation for code word. So C may be expressed as a partition row vector in terms of vectors m and b as. So this is the equation for C. C is equal to bm. So the portion of C is B, that is parity bits, and the other portion is m, that is message bit. So C is equal to matrix. In the matrix we have some portion of parity matrix, then we have message matrix. So C is equal to matrix B m. This is equation 5, and C is equal to, we can write B as BC equal to MP. So we write B as MPM. So we are taking M outside. So C is equal to M into PIK, where IK is identity matrix. So IK has a size of K by K matrix. So IK is identity matrix I0, 1 0 0 0, 0 1 0 0, etc. 0 0 1, which has a size of K. Okay. So we have CC equal to MPI. Okay. C equal to M into PIK. Then we can rewrite it as, which is equal to, C is equal to M into G. This G also very important. So we replace PIK with the G. So C is equal to MG. So this is the equation for code word C is equal to MG, where G is equal to PIK. Okay. So this can be written as G is equal to, so G have a size K by N. This is also important. G have a size K by N. P have a size K by N minus K. Okay. So G is equal to PIK and C is equal to MG. This is also an important equation. That is equation for code word C is equal to M into G. Message into G. This G is called generator matrix, and G is equal to PIK. Equation for generator matrix G is equal to PIK. Okay. The full set of code word is generated in accordance with the above equation. From this equation C is equal to MJ, we can create the full set of code word. Okay. So the generator matrix G is said to be a canonical form in its k rows are linearly independent. That is, it is not possible to express any row of the matrix G as a linear combination of remaining row. So G is a canonical form of matrix. It is linearly independent. That is, any row, sorry, by adding any row, we didn't get the other row. So it is linearly independent. The sum of any two code word is another code word. So the basis property of the linear code word is closure property. So the property of linear code word is closure property, because if we add two code word, we get another code word. This also we are called linear block code. Okay. So the closure property is, when we add two code word Ci plus Cj, we get Mig plus Mig. That is, we take G outside, we get Mi plus Mj. So Ci and Cj are code word and Mi, Mj are message vector. So the modulo to sum of Mi and J, we get similarly the modulo to sum of C and Cj represent the code vector. Modulo to sum of Mi and J represent the message vector. And we are, so we have the equation for C, code word C is equal to mg. Equation for B, parity bits, that is B is equal to mp. And we have equation for G, we are created generator matrix G, pik. Now we are creating another matrix, that is H, which denotes n minus k by n. Okay, this is also important, the size of G. The size of G is k by n. The size of H is reverse to that, that is n by, not is k, n minus k. Okay, so the size of G is k by n, that is for a n comma k block code, the size of G is k by n. For n comma k block code, the size of H is n by n minus k. Okay, it's reverse of that, n by n minus k, that is n minus k by n. Okay, we are converting. So this is k by n. Then the matrix H matrix is not k, instead of k we are writing n minus k by n. Okay, then H is equal to, can be represented as, we have represented G as pik, then we are representing H as, I will come here and P will go there, and similarly the size also changes. So some changes for I and P. So G is equal to pik, then H is equal to I n minus k p transpose. G is equal to pik, H is equal to I n minus k p transpose. So the identity metric has size n minus k. Okay. So this is so H is called a parity check matrix, and this is generator matrix having size k by n, parity check matrix having size n minus k by n. Okay. Equation for generator matrix is pik, equation for parity check matrix in minus k p transpose. Okay. Then next we have some proof, that is this H is called parity check matrix. Okay. So parity check matrix into generator matrix transpose. So H into G transpose is equal to H into G. We have H is equal to I n minus k p transpose, and G is equal to pik. So we are taking transpose, then we get p transpose ik. By multiplying these two, we get p transpose plus p transpose. This is modulo 2 addition. So when we add same terms, we will get 0. So Hg transpose is equal to 0. Similarly, that is 0 denotes n minus k by k is a null matrix. So that is Hg transpose is a null matrix. Then we have the reverse, that is Gh transpose. So for Gh transpose, the equation for G is pik, and equation for H transpose is in minus k p. By multiplying these two, we get p plus p, which is also 0. So it's also Gh transpose and H transpose G both are equal to 0. That is a null matrix. Okay. So we can create an equation for H transpose. So we have from equation 7, we have equation 7 C is equal to mg. So we can write C as C is equal to mg. Now we have, this is, for this C is equal to mg, we are multiplying with both sides with the H transpose. Then we get C into H transpose, mg into H transpose. Okay. Then we have GH transpose. We have GH transpose is equal to 0. So this term will become 0. So the equation for parity check matrix is C into H transpose is equal to 0. Okay. The matrix X is called a parity check matrix. Okay, of the code word, and it is called parity check equation. This is called parity check equation. Okay. Then that's about parity check matrix and generator matrix. Okay, we can graphically represent that when give a message vector to generator matrix, that is by taking this equation. This is the equation for parity check matrix, and this is the equation for generator matrix. Okay, Cc equal to mg. Now, if we are giving input to a encoder, m to encoder, we get code word. Okay, if we are giving C to the encoder, we get the null matrix. That is represented here. If you are giving a message vector for a generator matrix, we get code vector as the output, that is equal to mg. Then if you are giving a code vector to parity matrix, that is ch transpose, we get a null vector 0. Okay, so that's all about today's class. We have discussed what is linear block code, what is parity equation for parity check matrix, what is generator matrix. Okay, what is the equation for code vector, what is the equation for parity parity matrix, that is B is equal to MP. So that's all about today's class. Thank you.